equals to 0.693 into RB into C. Then we get the RB frequently 817. Then to ohm, 817 ohm. Choose nearest resistor. I choose the nearest resistor. RB is equals to 820 ohm. T of H frequently after using the formula 0.6. The formula is 0.693 into RA plus RB into C. Then we got RA is equals to 767 ohm. Then we choose the nearest resistor. RA is equals to 1 kilo 1 kilo ohm. Checking the actual duty cycle frequency, T is equal to 0.693 into RA plus 2 RB into C. Then T is equals to 0.083194. Then we need to calculate the frequency. Frequency is equals to 1 divided by T. Then the frequency is 12 hertz. We got the frequency is 12 hertz. We supposed to the 12 hertz. Then we will use D is equals to RA. For the formula is RA plus RB divided by RA plus 2RB. After calculation, we got 65.9%. Which is frequently 66%. So for the justification for using 50 kilo ohm. So the justification first point is it is closer to standard capacitor value, uses power filtering device, highest resistor keeps hitting the potential framing shift. Then capacitor is equals to 50 microfarad ensures accurate stable TH and TL values required to the display blinking. Then this is our circuit. Sorry, this is our circuit design. Where stable and we have used stable and mono-stable. Stable is equals to continuous blinking. This available. Stable means continuous blinking and this available, and the mono-stable means that triggered is steady output full. So we must remember that the 555 timer has no enable signal. It cannot maintain a constant output on its own. So I used a D flip-flop and enable reset signal. Thank you for now. I will describe about the answer number 3. We have taken from the question we have TH output and TH output and TL output B. Clock period is 1 ms. If TH greater than 4 and TL greater than 4, then we will set TH is equals to 4 and TL is equals to 4. From TH is equals to, from the question 2, we got TH is equals to 54.9978 and TL is equals to 28.322, which both are greater than 4. And TH 4 cycles and TL 4 cycles, total 8 state. And binary state encoding is used to present state register must be 3 bit. Since log base 2 8 is equals to 3. In other words, the present state and the next state signal must be 3 bit wide. Then the FSM design. Design. The state diagram starts with a so the FSM design, the state diagram start with the 0, which is due to idle and reset state. When go input goes high, the FSM moves to the 0 0 1, then 0 1 0 0 1 1. All producing output A, meaning the display is on. Then it moves those 1 0 0 1 0 1 1 1 0 1 1 1. it walks back to state 000 and waits for the next signal to go. Then I will describe about the state table. The state table shows a very every state transition in FSM. I have three columns for the present state, bit Q2, Q1, Q0, and three columns for the state N2, N1, and 0. The input is go, and the output are A and B. When reset is high, the FSM jumps to state 000 regardless of the current state. This is synchronous reset behavior. In state 000, the equal to 0. In state 000 with equal to 0, the machine stays 0 at t-equals 0. When go equal to 1, it moves state 1. From this transition, I derive the Boolean expression in for n0, n1, and n2 using some of the expressions. Then I will describe about the Verilog SDL code. For the Verilog SDL code, I wrote RTL in the RTL implementation of FSM and the module named timer FSM RTL. The module has three input. C clock for the clock, CLK for the clock, RST for synchronous reset. Then the next step is the implement using the assigned statements on the each bit for n as each equations derived directly from the Boolean sum and the mean terms I derived for the state table. For example, n as index is 0 catches 0 checks combinations like Q2 and not Q1 and not Q0 and go. So on for each valid transition, the present state register used and always block checked on. The positive edge of clock each rising clock edges QS takes the value N and S. Finally, the output of the logic. So finally the output of the output A is for state 000 These are the TH state. Output B is for 1 for state 100 though 111. These are the TL state. Both outputs are expressed as the sum and midterm as an statements. So here is the ending of the question number 3. Now I will describe about the question answer number 4. Answer number 4 is about the limitations. There are some drawback on limitations for the part 1 and 2. Limitations for part 1. So the first one is the system has fixed capacity for the 12 bits, which cannot be created without designing the circuit. The system for entry and the exit sensor, which may produce wrong counts due to multiple patients entering at once for false triggering. This is no error correction mechanism. So incorrect sensor data will lead to wrong ICU occupy. The counter may face overflow problems if the counter exceeds maximum limit. And the fifth one is the system only counts the patient, does not identify individuals. So accuracy is limited. So now I will describe the limitations of part 2. The 555 timer has no enable control, so it cannot maintain a constant output, causing possible distress. Then the timing frequency duty cycle is fixed, make it difficult to modify the system. The 7-segment display is not suitable for long word. The long word like bits available make the design complex. The system consumes more power due to continuous blinking. two separate timers may create synchronous issues. Improvements. Use Then we will use a higher bit counter, 8 bit or more. The support is large number of bits. It will support a large number of bits. Refresh sensor with the smart ID systems and the accurate counting. Then we will use LED or LCD displays instead of 7-segment displays for the better reliability. Reliability at a finite state machine FSM better control automation. Then impact of modification, the system becomes scalable and large hospital. For large hospital, accuracy increases significantly. After that, the conclusion of the question number 4 is that the conclusion is the original system is simple but has limited capacity, lower accuracy and hardware constraints. The improved system provides a scalable, accurate, and solution suitable for the hospital environment, real hospital environments. Thank you, sir.